yes, I'm going to be talking about code style sheets. I'd like to start off the presentation by pointing out that code is displayed uniformly independent of task. So programmers do a lot of things in their text editors, not only writing programs, such as writing, debugging, reading, refactoring, and presenting. And for the most part, all of these activities are performed over the same view of the underlying code. And our idea in code style sheets is to imagine a world where we use different views for many of these tasks. So to give a more precise example of what I mean, let's think about this small Haskell program, which is meant to count the number of non-commented lines of code in a source file. So in the upper right, we have an input, which has 4 non-commented lines of code. So we would expect this program to output 4. Okay? But this program has a bug, and that bug happens to surface as a type error when you put it through GHC. And so our programmer, maybe seeing the types, wants to apply a color by type style sheet to debug their error. So what this style sheet does is it applies a different color to each type, which also appears in the error. And in this case, the types aren't super important for understanding the error, but they see that the parse of the program looks a little weird. They expected is prefix of to be applied to filter, and it looks like it's not. So suspecting that maybe they're dealing with a parsing issue, they decide to apply a different style sheet. This one's called blocks, and it puts a box around every binary operator application in the program. And this helps them confirm that, yes, the parse is incorrect. So they use parentheses instead of $, and now the same style sheet shows the same program that's sort of in their mental model of what the parse should look like. Okay, but this program still doesn't work. And so they use a common debugging mechanism in Haskell called trace, which shows the values that flow through a particular expression in the terminal. And to understand trace better, they use a trace style sheet, which puts the values that flowed through the expression in line with the trace itself. And by using this tool, they realize that filter doesn't filter, it actually keeps. And so they put a not in front of the is prefix of to fix up their program. So this program now works, but of course, you're not done when your program works. They want to apply a linter style sheet to make their program more readable. And so what this style sheet does is it identifies sequences of infix operator applications which are read left to right or right to left. So since bind is kind of read left to right, but dot is read right to left, this style sheet is pointing out that there's inconsistency. So they might use forward function composition instead. And now that the program reads all left to right, the style sheet is more silent. OK, so what can we take away from this small example? One is that we saw a lot of views of the same program source code. And the views were of the source code itself. So we didn't have some view off to the side that was showing auxiliary information. We were showing a view of the source code. And secondly, we applied, in some cases, the different style sheets to the same program, the same document. So we could think of an analogy here to maybe an existing technology. In this case, I want to think about HTML and CSS. So we also have this thing called HTML, which takes the role of a document, the AST. And we also have these things called style sheets, which can apply styles to the same document in different ways. So maybe we're done. We can realize our goal of code style sheets using an existing technology, CSS and HTML. But in our paper, we identified 2 problems with this approach. And the rest of the talk is going to be addressing these 2 problems. So the first problem is called the 2 trees problem. And this problem arises when we think about how we want to convert our abstract syntax tree into a view tree, so HTML. And in some cases, this transformation kind of is morally equivalent to the identity function. We're keeping the same structure from the AST and just sort of putting it into HTML. So that's like our blocks style sheet. But in other cases, our trees look totally different. So in our trace example, we added some extra information to the view, which was not present in the AST and arguably should not be represented in the AST. It's just a view. And furthermore, once the view is generated, the user might want to apply styles to their views. Okay? In the limit, they have to write a different style sheet for each of these views because they might have different structure. But our goal in code style sheets is to apply styles to the source and have those styles propagate through the view function into the various views that the programmer might want to use. OK, so the idea is that the programmer writes one style sheet which can style many different views. So to be more precise about this and to give a concrete example, let's think about a really simple AST type. Let's suppose we just have lists of tagged integers which are either tagged left or right. And suppose we wanted to view this list like this, where we have an Arabic numeral followed by a tally mark representation of the number. So we might write a function called makeView, which goes from AST to HTML, and maybe our HTML looks something like this. So let's say we wanted to do some styling task now. We wanted to color all the left numbers orange. Well, the way we might do this without code style sheets is by modifying our view function, scrutinizing each value in AST. If it's left, we add one class. If it's right, we add a different class. And then we could use those classes to style our numbers orange. OK, so what if we then wanted to box left square numbers? So again, we have to add a clause in our view function which scrutinizes left numbers, and only if they're square, then we add another class. But there's a bit of a problem here, which is that increasingly style is being decided in our view function, not in the style sheet. The styles that we apply are determined by the view function. And so what we want to do to correct this is we introduce some kind of bidirectionality between the abstract syntax tree and the view. We add this backward path, which allows the style sheet to reference both values in the AST and structure in the view. And so instead of targeting HTML, we're going to target this thing called HTMLP, HTML with provenance. And here's a little sketch of what that data type might look like. So it's just HTML with all the regular stuff, but we add this path, which points into a value of the AST. So now that we're able to scrutinize values in both the view and the source, we can write style sheet rules which look like patterns which match the AST. So we can now write that all left numbers should be colored orange like this. And we could add predicates that scrutinize the argument of the left constructor, styling left square numbers with a box. OK, but what are the semantics of these style sheets? So let's think of another example where we want to color all variables orange. So this is a style sheet that would accomplish that task, where we select all variable nodes in the AST, and then we apply some color property to them. So here we see the AST, and to the right we see a view. And then we also see that that view has been enriched with paths, as I described in the last slide. And our process for evaluating the style sheets is simple. We just traverse down the view tree and follow these paths. And some of these paths will match values in the style sheet. So this one doesn't match because do is not var. But we can continue to traverse down. And eventually we find a var which does match. And when we do find a match, we just take those properties and apply them to the corresponding node in the view. And that's how style sheet evaluation works. We do this for every rule in the style sheet. So here's a much more complicated style sheet, which implements part of the linting example, which I gave earlier. And I want to use this example to talk about our second problem, which is the layout problem. So those familiar with CSS might know that CSS operates on a rich notion of defaults. And one such default is the so-called display property, which describes what algorithm we should use to lay out children of an HTML element. And we have a few options to choose our display property. Here's an option where we used inline block. And we can see that if we use inline block to style our programs, we have a bit of a problem, which is that the program text can move around. Because we force every expression to be in a box, the text sometimes moves from the raw text above it. So OK, that's fine. Maybe we choose display inline instead. Now the text is in sort of the right place, but display inline prevents us from showing structure. So we can't see at a glance that get contents and bind should be an expression that surrounds the orange stuff. So we come up with our own display property called sblock, which attempts to both preserve the text's original location and also show structure. And the way that this works is that instead of surrounding each expression in a rectangle, we surround it in something called an S-block, which is inspired by the way that text selections are drawn in a lot of editing interfaces. So what we've done is we've made this shape nestable. And we defined an algorithm to do this, which proceeds in 3 steps. So first, we take all the text fragments, all the little pieces of text, and flatten them out. Then we insert these little things called H-gadgets in between some of the fragments to make space for the structural visualization. We do the same thing in between lines. So going into more detail about each of these steps, basically the way we insert H-gadgets is in direct correspondence to the shape of these S-blocks. So before the first line of an S-block, or before the first fragment of an S-block, we insert some H-gadgets. After the last fragment, on the first fragment of a line, and on the last fragment of a line. And we do the same analogous thing for horizontal lines as well. Okay? And once we've inserted these gadgets, it's pretty easy to come up with a polygonal outline, which gives us the visual appearance of the S-block. And the rest is post-processing. OK, so we implemented the system in about 5.7 thousand lines of Haskell. That includes a small Haskell subset interpreter and type checker, which we use to generate examples, and 1.2 thousand lines of style sheets written in our system. We have a bunch of examples in our paper, but here are some of my favorite ones. One where we show and hide and different parts of the code, maybe in like an educational setting. Here's where we implement this feature, sometimes called semantic highlighting, where the use and binding site of variables are colored with the same color. Here's another one called heat map, where we give each expression a different color based on how many times it was evaluated in a certain run of the program. OK, so in this work, we figured out how to make read-only displays using code style sheets. But in future work, we want to improve these layout algorithms to be able to express more complicated visual ideas. And much of this work has already been done in our recent WIST paper. So I'd invite you to look at that if you're interested in the layout portion of this work. And then, of course, in the future, we want to integrate this kind of technology into editors so that programmers can enjoy code style sheets as they edit their programs. OK, that's all I have. Thank you.
Can you hear me? Oh, yeah. I was curious about this last bit of future work in particular. Do you foresee any challenges with like interactive editing and CSS, these like style sheets at the same time in terms of like user experience, like delays in updating the highlights or like resizing during the code editing process?
Yeah, so I think one of the main motivations for caring about this layout problem, where we sort of don't want either boxed stuff or too, well, this I guess is OK for editing because this is what we're used to. But if we want to show structure as well, I think one of the main considerations for why we care about the layout problem is that when the user is editing, we want that experience to be similar to what they would experience if they didn't show any structure at all. So I think keeping the text close to where it would be ordinarily is a really important consideration. So that's sort of the main motivation for this stuff. Of course, there is a lot of engineering work to be done to make sure that style sheet evaluation is fast and that there's not delays. But we haven't thought about that too much yet.
Thanks.
Hi, thanks. Great talk. I was curious how this relates to wrapping or pre-printing the code, because in the examples you showed, correct me if I'm wrong, the code comes in already formatted to fit whatever line width you're at, and then you're just styling on top. But I do know that like modern CSS features allow you to control how that wrapping happens, at least in the context of text. So do you have ideas for controlling wrapping through CSS-like properties for code?
Yeah, so I think maybe one angle you're getting at is we saw a different paper earlier in the session about code style in the context of how you format your code. And that's certainly another thing that style sheets could target, and I think that'd be really interesting. But our work so far doesn't really think about how